Hi, hello. In this video, I'm going to help you understand certain tools associated with measurement system analysis, particularly tools such as bias, repeatability, reproducibility, and Gage R&R. So these are the tools we are going to learn in this particular video. So the learning objectives goes like this: bias, repeatability, reproducibility, and then Gage R&R, which stands for gauge repeatability and reproducibility. So let us understand all these things. So first of all, why measurement system analysis? The Six Sigma project team aims to reduce the process variation because it is fundamentally the process variation which causes defects in your product. So the Six Sigma team is aiming to reduce the process variation. At the same time, if the variation is due to the measurement, what will happen? The variation due to the measurement is called measurement error. Measurement error is an illusion. The measurement error will hide the reality. So you should not allow the illusion to hide the reality. So you should find a way to control the measurement error. And that's why it's important for you to conduct measurement system analysis and then correct and improve the measurement system. And then only you should collect the data and then proceed with the calculation of baseline and analysis. So fundamentally, measurement system analysis helps in reducing the measurement error. So doing a project, doing a Six Sigma project, solving a complex problem is equivalent to driving a car in a highway. When you are driving a car in a highway, it is very important that you keep your focus on the road and then drive the car. If you are not able to focus properly on the road, then definitely it will lead to accidents, injuries, and then you will not reach the destination. Similarly, when you are solving a complex problem, your focus should be on the problem. So you should not be distracted, from seeing the problem. If you allow the measurement error to dominate, what will happen? Your focus on the problem will get distracted, and which means you cannot drive the project to success. Your project will get delayed, and then eventually it may fail also. So measurement system analysis will help you to minimize or reduce the measurement error. Thereby your data becomes credible because we could see the problem only through data, and so it's very important we collect data without error. And see here in my slide also, the windshield is covered by the water droplet. When the windshield is covered by many water droplets, what happens? Your vision is getting affected. Similarly, when your data is contaminated with error, your focus on the problem will get distracted. In fact, you will not be able to understand the problem correctly. And that's why MSA is very important. So MSA, measurement system analysis, ensures the Six Sigma team focus accurately on the process variation and ensure the improvement efforts are used efficiently to reduce the process variation. Otherwise, you may put efforts thinking that you are actually reducing the variation, but actually, it is not. So you can see better and understand the process condition better with measurement system analysis. So that's why you need to learn these tools: bias, repeatability error, reproducibility error, and then Gage R&R. So what is bias? Bias is nothing but the difference. Bias is nothing but the difference. Let us say you are measuring, a characteristics. Let's say the characteristics is dimension. The dimension is 100 mm, and you are asked to measure 100 mm. So you are actually measuring, and your reading says the characteristics, the dimension of the product is 102 mm. But I have given you a standard workpiece. The dimension of the standard workpiece is 100 mm. But what are you, entering in your data sheet? The 100 mm dimension is entered as 102. Now there is a difference. Your observed value is 102, but the true value is 100. Now this difference is called bias. Another example. Now the time is, let us say 9 a.m. in the morning, but my watch is showing 9:05. Now what is that? Now the observed time is 9:05, but the actual or the true time is 9 a.m. Now what's the difference? 5 minutes. This 5 minutes is called bias. This 5 minutes is called bias. If the bias is low, your readings are becoming accurate. If the bias is zero, you are 100% accurate. If the bias is more, you are becoming inaccurate. Hope all of you understand what is bias. Bias is fundamentally the difference between the observed value and the true value of the characteristics which you are measuring. See here, there is an example. A standard workpiece with a known value of 25.4 mm is checked 10 times. How many times? 10 times. And the readings are recorded by the quality inspector in this manner. See here, 5 readings in the first row and then another 5 readings in the second row. How will you calculate the bias in this case? When you have multiple reading, when there is only one reading, you find out the difference between observed value and the true value. When there are multiple reading, first convert the multiple reading into a single value. How will you do that? By calculating average. Find out the average of the 10 reading, which is called X bar. Add all these numbers, all these values, divide by 10. So what is the average value? 25.4051 mm, right? Because the value is in mm. So 25.5041 mm. Now what is the bias? The observed value minus true value. True value is given as 25.4. Now what is the difference? 0.0051. This 0.0051 is the bias in your reading. Right now, your bias is positive bias because you are reading, the average of your readings is more than the true value. So the bias is called positive. If it is lower than the true value, the same bias will be called negative bias. And generally, generally, bias is expressed as a percentage of the, process tolerance. See here, the process tolerance is given plus or minus 0.25. Plus or minus 0.25 means the total tolerance range is 0.5. So the 0.0051 is compared against 0.5 and then the ratio obtained is multiplied by 100. So what do I understand is the bias is 1.02% of the process tolerance. So bias is expressed as a percentage of the process tolerance. Hope it is clear. What is bias? The bias is the difference between the observed value and the true value. And goal is bias should be 0. In case bias is not 0, then what we do is we will calibrate the equipment. We will calibrate the equipment. We will again, try to do everything that is possible from our end to correct the measurement system, including the calibration, and then we will remeasure the characteristics. All right. Another important term, repeatability. What is repeatability? See here, the previous time. There are 10 readings. 10 times the product is measured. 10 times the product is measured. But the product is same. Measuring equipment is same. Appraiser is same. Measuring procedure is same. Measuring environment is same. But look at the reading. The readings, are not same. All the 10 times you are not getting the same reading. There is some variation you can observe. That is called inconsistency in the measurement. This is called inconsistency in the measurement. An estimate of the inconsistency observed in a single appraiser's reading is called repeatability error. That is written here. When I say inconsistency, it is repeatability error. Suppose if you can measure consistently, then you are highly repeatable. Hope you get the point. Repeatability is good, but repeatability error is bad, right? So repeatability is the consistency of a single appraiser to measure the same part multiple times with same measurement system. It is related to the standard deviation of the measured value. That means if you are measuring a part multiple times all your multiple readings should be same, should be close to each other. If it is close to each other, then you are repeatable. If the readings are not same, if they differ by a large amount, then the error committed by you is repeatability error. You will be considered an inconsistent appraiser. All right. So now, if you, in order to visualize the repeatability error, what you need to do is you must visualize your data. When you visualize your data, generally any continuous data will follow normal distribution. We know about it. And if the error is too much, you know what will happen? The curve spread will, get increased. See here or come here. There are two gauges used, gauge A and gauge B, right? And for the same product, gauge A is giving reading like this, black color one. But the gauge B reading are like this, mean the wider, which means gauge B is not repeatable. However, gauge A is repeatable. So you can estimate the repeatability error by measuring the spread of the process, the spread of the data. The spread of the data can be measured in terms of standard deviation. That is why it is, this statement is included. The repeatability is related to the standard deviation of the measured value. If the standard deviation is more, you can understand the repeatability error also more. If the standard deviation is less, you can understand the repeatability error is less. That means you have become consistent. That means your readings are repeatable in nature. Hope it is clear. Now comes reproducibility. If there are multiple appraiser, let's say I am collecting, data, or I am measuring a part. Same part you are also measuring. And I am saying that the measured value is 102. And you are saying that the measured value is 105. Now there is a disagreement between you and me. Same thing is possible in any project when the team members or the appraisers are collecting data. When there is a disagreement between the appraisers, that is called reproducibility. That is called reproducibility error, right? So whether I am collecting the data or you are collecting the data or someone else is collecting the data, since the product is same, all of us should give the same reading. If this is not happening, the error is called reproducibility error. Look here, there are three appraisers. Appraiser 1 represented in black color, appraiser 2 represented in red color, appraiser 3 represented in green color. Now, appraiser 1 and 2 says, the measurement is, appraiser 1 says the measurement is here or the measured value is here. How do I conclude the appraiser 1's reading? I consider the average of the appraiser 1's reading. Average of appraiser 1 is here. The average for appraiser 2 is here. But average of appraiser 3 is far away from 1 and 2. That means appraiser 3 is not agreeing with 1 and 2. Similarly, the agreement between 1 and 2 is somewhat better, but there is a small amount of disagreement. So this kind of disagreement between the appraiser, among the multiple appraiser, is called reproducibility error. It's called reproducibility error. And now read the definition. Reproducibility is the consistency of the different appraiser in measuring the same part, with the same measurement system multiple times, right? So reproducibility is good, but reproducibility error is bad. If you want to estimate the reproducibility error, then you simply measure the standard deviation of the appraiser's averages. See here, 3 appraisers are involved. So how many averages you will have? 3 averages. So calculate the standard deviation of the 3 appraisers' averages, and that standard deviation is an estimate of your reproducibility error, right? So reproducibility means the inconsistency in the readings of multiple appraisers, or the inconsistency between the appraisers. Inconsistency in the readings produced by multiple appraisers is called reproducibility error, and the inconsistency within an appraiser reading is called repeatability error, right? So we must control both, but we cannot eliminate, because this is like rule of the game, rule of the nature. Always measurement error will populate, right? And so precision error means it is the combination of repeatability error and reproducibility error. That means you must combine repeatability error and reproducibility error, and both put together is called precision error. It's called precision error. So precision error is repeatability error plus reproducibility error. Always precision error is compared against the working range or the part tolerance to estimate the gauge R&R value. So what is gauge R&R? Gauge repeatability and reproducibility. The gauge R&R is nothing but a ratio between the precision error and the part tolerance. So precision is the numerator, tolerance is the denominator, and this is called precision tolerance ratio. The other name of the precision tolerance ratio is gauge R&R. So in gauge R&R, the numerator is precision error, denominator is USL minus LSL, because USL minus LSL is the range of tolerance, and this ratio should be less than 10%. This ratio should be less than 10% to consider your measurement system is good. So this guideline has been, set by an organization called AIAG, Automotive Industry Action Group, and it was set long back, but even valid, considered valid even today. And it is used not only by automotive industry, but also by all the other industries, even IT, software, service industries, and the rule is common. So gauge R&R measures combined repeatability and reproducibility that defines the capability of the measurement system. If the gauge R&R value is less than 10%, the measurement system is considered capable and good. If it is 10 to 30%, conditionally acceptable. If it is more than 30%, never acceptable. You better throw away the data and better don't collect the data and seek for improving the measurement system or replacing the measurement system, right? In any case, when the measurement system's error, which is the gauge R&R, is more than 30%, don't use such measurement system, right? So what is that we learned in this session? The main objective of the measure phase is to validate the measurement system and then measure the baseline performance, right? Before calculating the baseline, before collecting the data, we must validate the measurement system. And MSA terminology we learned is bias and then gauge R&R. And if the bias is more, then you can think about calibrating the gauge. Actually, you must calibrate the measuring equipment so that you can bring down the bias to 0. And also the calibration procedure, maintenance of the equipment, and moreover, the frequency of calibration are important for the stability of your reading, right? If after calibration, if the gauge continues to provide you bias-free reading, then your reading can be considered stable, right? So to ensure the stability, you must also have, calibrate the equipment, measuring equipment at an appropriate frequency. Gauge R&R should be less than 10% of the interest zone. I mean the working tolerance, part tolerance. And if it is in the range of 10 to 30%, the measurement system is considered conditionally acceptable. But in any case, if the gauge R&R value is more than 30%, the measurement system is considered unacceptable and don't collect data using such measurement system. And as I already mentioned, working range is either the part tolerance. If the part tolerance values are not known to you or not available, then you can consider steady variation in place of part tolerance. Steady variation is nothing but the range of your readings. The range of your reading is considered steady variation. Hope you are able to understand the tools bias as well as gauge R&R, and see you with some more interesting tools in the next video. Thank you.